I've been working with Professor Pober and doing research on the Epoch of Reionization, which I'll get into in a bit, but just generally I do cosmology research with neural nets. I expected there to be fewer astrophysics people here, so I started pretty basic. We've got the whole history of the universe, Big Bang kind of, universe is expanding. And the part that we're kind of interested in with my research, and the part that I'm going to be talking about, is the Epoch of Reionization, which is right after the Dark Ages. So that's the time. The Epoch of Reionization is the period after the cosmic dark ages, where the first stars and galaxies are forming. Energy from new star formation is ionizing neutral gas. And we can observe this time period by looking at the 21 centimeter line, which is the emission of neutral hydrogen. I'm going to kind of blast through some of this stuff pretty quick because I think we have a lot of astrophysics people here. So yeah, 21 centimeter cosmology is when the state transition of the hyperfine energy levels of the ground state of hydrogen releases a photon. And that photon is 21 centimeters. And you can use it at different redshifts to trace atomic hydrogen. And so using the 21 signal, we can look at the epoch of reionization and any time period that has this hydrogen signal by looking at this 21 centimeter wavelength and the different wavelengths that it is redshifted to. And that's a way we can actually sort of peer through time. And so this is in the radio, so we observe the redshifted 21 centimeter line with radio telescopes. Depicted here is the Hydrogen Epoch of Reionization Array, which is HERA, that is currently still under construction, but it's kind of going to be really useful for observing the epoch of reionization specifically. And it does so by using radio interferometry. So we want to use radio interferometry because using a normal telescope at very hot, like large wavelengths would be, you would have to create like an impossibly massive structure. It would have to be like miles and miles and miles wide. So you can't do a single telescope. Instead, you can actually set up pairs of antennas that will create an interference pattern as they observe the signal at different positions. And if you've ever taken an optics class, you know that a diffraction pattern is just a Fourier transform. So when we have two antennae that are taking a sample and creating this diffraction pattern, we can sample one Fourier mode of the sky. And so if you have a bunch of arrays of telescopes, you can kind of get a very good picture of the Fourier space, and that will tell us things about the actual space. So I have this in summary. Radio telescopes observe the spatial power spectrum of neutral hydrogen depending on the frequency of the signal. So here's kind of an example of that. But you would think that if we could just observe enough Fourier modes and then Fourier transform the observations, then we could just look at the EOR. But it's not that simple because we also have noise that is in Fourier space. We have foregrounds that are like radio sources that are closer to us than the epoch of reionization. Those signals are also much louder, like stronger amplitude. So we have to sort that out. This is called the wedge. This is a basically all of the Fourier modes that we miss out on because of galactic foregrounds. And that's kind of like a huge problem in EOR radio research because that's because it's not just like a portion of the sky is blocked off. Entire Fourier modes are gone, so it's just like a ton of data is missing, and you can actually see that how this data is, you know, in this image, but we can't see it because all the foregrounds are in the way. So this becomes kind of a non-trivial problem of extracting information from our radio readings from the EOR. How do you know what's a foreground and what's not? How do you get information from data that has such high signal noise to signal ratio? And so these are some things that we want to know about the Epoch of Reionization. We want to know how long it was. These are all things that we have constraints on, but don't know exactly or exactly enough for science. We don't know how long it was. We don't know exactly when it took place, and we don't know the curve of sort of the acceleration of how the hydrogen was reionized. We don't know if all the hydrogen was reionized like steadily at the same rate, or if it started slow and then picked up, or if it started really fast and then leveled off. This figure that I have is as of 2017, a collection of all of the various studies constraining these properties. And as you can see, there's still a pretty wide range of possible histories in this curve. It is not very highly constrained at all. So what does this have to do with machine learning? That was all kind of just background to get you caught up on what problems we're interested in solving. This problem seems ideal for machine learning because it's a very messy data set that has some sort of pattern that is physically very complicated, but could be much easier for a machine to look at and extrapolate things from it. The difficult, so we want to try and use a machine learning algorithm to find these cosmological parameters, such as the duration, how long it was, such as the midpoint when it took place. But the problem is machine learning algorithms require training data. And since we don't know the actual duration and midpoint of the Epoch of Reionization, that we technically don't have any real training data. So how can we create a machine learning model with no training data? And this is probably a problem that's applicable to a lot of places in physics where we want to regress on parameters that we don't know. So what our solution is to train on data that we get from semi-numerical simulations. So instead of training on the exact same data that we want to predict on, we are training on data that is as close as we could possibly get to it. So what I've kind of loosely termed the fake data, our semi-numerical simulation data, is generated with simulations of reionization scenarios. So we create a sort of false universe with our own initial conditions, let that play out, and then take snapshots of what we would see using HERA or another radio telescope. So these simulated images are kind of ideal for machine learning because they become pre-labeled. We set the parameters at the beginning of the simulation, and so we can just train on that. We can create a simulation that has like a redshift of, 10 midpoint, for example, and then we can create like a bunch of those that have that and then train on all of those. And we can get a really diverse sample that way. The one trouble with this, yes, what?
Can I ask a question? Are these created with 21 centimeter fast?
These are not actually created with 21 centimeter fast. There is research being done in I'm joining, sorry, my thoughts. Other people are doing that research. I'm not doing that research. I'm using semi-numerical simulation that, I don't know if you know Paul LaPlante. He wrote a paper and he has a simulation. These are all of these are his simulations, and I've been working with him on this whole project. But yeah, that is a 21 centimeter. One project I at least know of is somebody is trying to see how these models do across different simulations. So they're training on one semi-numerical simulation and then predicting on another and seeing how they do to avoid that overfitting. So yeah, the one problem with this issue, which actually relates exactly to what I was just talking about, is we need to make sure that this is not overfitting to this data, that this that our model is not learning these simulations really, really well to the point where it can't predict on real data. And so that's a problem that we're going to have to address at some point, but we're still in pretty early stages of this. So now I'm going to transition into the more theoretically machine learning aspect of all of this. We're training on images, which is sort of a whole another beast of machine learning thing. A typical machine learning approach to something will be to take any sort of input. I just have image here because that's what I typically work with, and connect each sort of node of that input to each node of the hidden layer, and etc. So you have the computer is storing a weight for each one of those neuron connections. And when you have a lot of weights in both your input and your hidden layers, that ends up being a very, very, very large array. So dense networks don't really work very well for when you want to predict on images because it's overkill. Here's the example I have here. Given that you have some image that has width W, height H, and then channels are in typical ML stuff. Channels would be like color channels, but we actually use we'd have like 30 redshift channels. Typical. Can you hear me? Sorry, I had internet connection unstable for a second.
Yeah, we can hear you now.
Okay. Well, what was the last thing I said before I cut off?
You were sort of just getting into like what the channels were about.
Oh yeah. Okay. So in a typical image network, the channels would be color, but we use redshift. So say we have like 30 redshift channels, and like say a 512 by 512 image, then you have 512 by 512 by 30 by however many neurons you have here. That's like that's about like 7 million neurons that's increasing as you increase this inner layer here. And that's a lot for the computer to handle. And it's also overkill. And it also doesn't give you really any information about, it doesn't give you spatial information. It gives you information about each sort of individual pixel, but each pixel has no way of knowing what pixels are around it. So it's not very good for images. So what we're using and what image recognition does in machine learning most of the time is a convolutional network. So instead of each input being connected to each output, you have a matrix that you convolve over your image. This is a 2D convolution here, so you're just doing the convolution for this part, and then you kind of mirror that for every channel. And then you just slide this matrix over your image, convolving as you go, and then each output from that convolution is a pixel in your next layer, or an input in your next layer. So instead of having like millions and millions and millions of neurons that the computer has to store, you're storing like however many filters you have times the size of those filters. So if you have, say this is 3 by 3 by 30, and you have 64 of them, that's just 17,000 weights. So much more efficient with computing resources. And also it gives you spatial information because these kernels, sometimes they're called kernels, these filters are usually 3 by 3. They can also be 5 by 5 or 7 by 7, any odd number, but they sample all of the pixels in an area. So they actually will tell you more spatial information. And the weights that we're training are the elements of these matrices. So you actually get spatial information by having a convolving matrix that you move around. So how do we apply this to studying the epoch of reionization? So what I did, and this was my research, is that I trained one of these convolutional networks, these sort of image recognition-based networks that use convolutions to identify spatial information in images. And I trained one on the semi-numerical simulations of the 21 centimeter data, the epoch of reionization scenarios. We had about 1,000 images, so about 800 once you do the training testing split to train on. And then we have our model. Yeah, I didn't want to get too into this, but oh, actually, let me go back. This hyperparameters here is like the bulk of the work involved in research like this. It's a lot of just training models and seeing if they look good, and then training more models and seeing if they perform better or worse, and kind of trying to zero in. It's very much more of an art than a science on hyperparameter optimization. I don't have much to say on that beyond it's a lot of trial and error. And hopefully we get predicted cosmological parameters out of that. Kind of wanted to talk about some challenges that a lot of machine learning algorithms face, and that might be very important in physics research, including the research that I'm doing. So a huge issue is overfitting, which is basically, is the model learning the data too good? In the case of my research, I'm very worried that the model is learning the simulations that I have very good, but then is not going to be able to generalize that to actual data. And so there are ways you can test this. This is a pretty common problem and discussion point in the machine learning community. It's probably familiar to a lot of you. I thought I'd throw it in because it's pretty important. There are a lot of ways you can mitigate this, including like having dropout layers and being really careful with your validation data, and making sure that you're not training for too long and your data set is diverse enough. So that's a pretty general problem, but I think it's pretty important in physics where we are trying to, especially with my problem where I'm trying to take one thing and generalizing it to another. And then I think the thing that's more specifically relevant to like physics research and science research using ML in general is error propagation through networks. So when you think about machine learning networks, you're going to have, some uncertainty with the input data, but then you're additionally going to have some uncertainty that the model inherently has in it, that it will apply regardless of the input data. And so a topic of research in machine learning right now is sort of how do we measure the inherent bias of a model? One technique that we were playing around with in our lab is extended Kalman filtering, which is that EKF here. That wasn't really my part of this project, so I don't know a ton about it, but it's something to do with the gradients with the machine learning neurons. But all this is to say that like it's important to consider when doing machine learning research the inherent bias of any given model that you have, and that's something we're thinking about a lot too. Oh yeah, okay, so these are my results from last summer with my convolutional neural net trained on semi-numerical simulations. These are predictions on the sort of same class of simulations. So we still have no idea how this would generalize to HERA data or to like real 2100 centimeter data yet. This is with foregrounds applied. This is with the wedge that I was talking about removed. But this is without noise modeling, which is a very complex topic actually in radio astronomy, just because noise exists in the Fourier space. So the results are very promising is the gist of it. It's not overfitting. Duration's a lot worse than the other. Oh, I should probably explain what each one of these is. So this is mean. This is the we're predicting on, given a bunch of images of the epoch of reionization, can this model track when 50% of the hydrogen in these images is reionized? And remember that these have foregrounds applied, so you can't just find the image that's closest to having like 50% of the hydrogen ionized in it, because the foregrounds are gone. So like a ton of the information is missing. And then this is, oh, I actually might have mixed these two up, but one of these is the midpoint, which is it's sort of halfway through the duration. It's like when exactly the EOR took place in the history of the universe. And then duration is usually defined as the redshift, where 75% of the hydrogen was ionized minus the redshift, where 25% of the hydrogen was ionized. And the one really interesting thing is that our model does significantly worse with duration. And there's a lot of sort of thoughts about why that is. It might have something to do with like how we're segmenting our images. It might just be that the 21 centimeter data doesn't contain as much information about duration that the model is able to pull out. But yeah, that's actually something we're thinking about right now. So yeah, current research this summer is, I don't really have time to give like a in-depth thing about the kinetic Synev-Zeldovich effect, but it's basically an effect that takes place during the EOR that is like bulk inverse Compton scattering of high energy electrons off of the CMB. And so it's basically kind of annoying to CMB researchers because they have all these anisotropies in their data that they have to get rid of, but it's really great for Epoch of Reionization researchers because a lot, the KSC, the only period in our history where we think that the KSC signal was really strong was during the Epoch of Reionization, where there was like a lot of bulk motion of these electrons. So EOR researchers could potentially take information from these perturbations in the CMB and learn things about the epoch of reionization that way. So my research right now is involved with like training sort of in dual input streams with both the kinetic Synev-Zeldovich effect data and also 21 centimeter data, and seeing if we can improve our results. Because remember how I was saying the duration, we're not able to predict on that as well. We're not able to predict on how long the EOR lasted based on our 21 centimeter data very well. The KSC effect is supposed to be really strongly correlated to the duration of the EOR. So we're hoping that that will contain a lot more information about it. We have some this is like stuff I'm doing right now, so I don't have a ton to show. But like here's a model where blue is I trained only on the 21 centimeter data, black is I've trained on both, and then green is I just trained on the KSE data. And our current thought is that we might have to degrade our 21 centimeter data a little bit, which I feel like all things considered is a good thing to have our models predicting too well for us to see any real difference between the KSE, the addition of KSE data. The thing that makes me very optimistic is it does look, if you've spent as much time staring at these graphs as I have, it does kind of suggest that the 21 centimeter and KSE predicts a little better on duration than the 21 centimeter only, which makes sense given that the KSE contains a lot of information about that. And so what we're sort of doing now is looking at alternate ways of combining these two pieces of data. With convolutional neural nets, it's kind of interesting because there's like it's feature recognition, so it's kind of trying to figure out how to combine these feature recognition matrices in ways that make sense and in ways that maximize what the model can learn. And we're also looking at potentially going from 2D convolutions to 3D convolutions because that will maintain some of the temporal data involved in the redshifts a bit better. I could go into that a bit longer, but that was something I was just researching yesterday, so I'm not super knowledgeable about it yet. But yeah, and the sort of eventual end goal is to use these models to regress on these cosmological parameters in real data. And that's my whole presentation. I might have sped through that a little too fast. I have a tendency to talk very quickly. But if I was unclear about anything, I would love to answer questions.
Yeah, thanks. That was a great talk. Yeah, I guess I do have some questions more about perhaps your implementation.
For sure.
Could you talk a little bit about your architecture and sort of what you use? Obviously, it's a CNN, but do you have any details about sort of how many layers? What did you try? What worked? What didn't work?
So we have about 4 stacked layers where each stacked layer is a 2D convolutional layer, a max pooling layer, and a rectified linear unit layer. We tried to include dropout layers to reduce the overfitting, but they degraded performance like a weirdly large amount. So we removed those. Same with batch normalization, we couldn't get that to work. So it's actually a surprisingly simple model. We're kind of just, it's a fully convolutional network. So we actually don't have any dense layers in it at all. Yeah, which is mildly unusual. We basically just take advantage of the max pooling layer's natural reduction of the dimensionality of it to the point where it just reduces everything down to like 1 by 1 by 3 because we're looking for 3 cosmological parameters. So,
did you ever consider using any state-of-the-art algorithms like AlexNet, ResNet, DenseNet, VGG, something like that?
That'd be cool. I don't think I'm far enough along to consider something like that, and our model is honestly performing so well with the data that we're giving it that we'd probably have to encounter more serious problems with our current approach before we would consider other algorithms.
Yeah, if you do run into a roadblock, I suggest looking into ResNet. I've found that to be, it solves every problem I've basically ever thrown at it for the most part.
Yeah,
but yeah,
the magic of ResNet.
I've only seen fully convolutional stuff like once before implemented in like physics, so that's kind of neat. Although it makes sense in the setting, of course.
The original sort of conceit of why we wanted it, here, I'm actually going to stop screen sharing. the original conceit of why we wanted it to be fully convolutional was A, for the extended Kalman filtering, which was not really my part of the project, so I don't want to talk too much about that. But it's an error propagation technique, and I think it's mathematically a lot easier through convolutional layers, was my understanding. Might be wrong on that, but the other idea was that we want, additionally, originally, I was working with Josh Kerrigan. I don't know if either of you knew him. He graduated last year. He was also working on this project, and his initial idea was to be able to kind of resize images and still be able to train on them. So he was trying to train it so that like a 20 by 20 pixel image would be sort of predicted on the same way as like a 30 by 30 image or something like that. He wanted to be able to like dynamically resize all of the inputs and still get good results, but it ended up being kind of a pain and not working super well. So we have this sort of artifact of having a fully convolutional neural net because we wanted to do that, but then it kind of just never ended up happening. Our model was working really well, so why change it?
Why did you want to, so the images come naturally like 30 by 30 and you wanted them in the format 20 by 20? Is that roughly?
No, so the idea was actually, so our images are all 512 by 512. And the idea was we wanted to be able to give the model any size of image, any snapshot of these original images, and it could predict on that. So if you sort of, took the metaphorical scissors and cut out like an inch size chunk versus a 2-inch size chunk or a 1.5 size chunk, you could all throw it at the same model, at the same trained model, and it would predict it all the same. That was the idea. It didn't work super well. That was Josh's part of the project more than mine, because I don't really know why it didn't work, but we kind of abandoned that. So we actually are just training on 256 like subsamples of images now. Oh, I remember why we wanted to do that. We wanted to do that because it would like create more data for us, because these simulations are kind of take forever to run. So we wanted to, like, by subsampling our images that are like 512 by 512 into, small 256 random chunks, we sort of implicitly get more data that way. Yeah. data is everything. Big data.
If you want to make more fake data, you can do something like a GAN, I guess, right?
Actually, don't know what that is.
Oh, a generative adversarial network.
Oh, yeah.
Type of autoencoder. Well, sort of
Yeah.
more complicated. Have you thought about doing anything unsupervised with 21 centimeter?
It would be interesting. I think the fear is that we would get some result and then just not really know what the physics was behind it, and then just be like, well, that's weird. I think we kind of want to make sure that everything we're doing is like physically based first and foremost. And also I'm pretty new to machine learning, so I wouldn't, and I'm also pretty new to 21 centimeter research, so I probably wouldn't even know where to start or what to look for with that.
Yeah, so an idea that just came to me is, by coincidence, I gave a talk on this a while ago, is it seems to me like, the hydrogen refraction, during reionization is sort of like it's a phase transition, right? Mm-hmm. And so one thing that's known is that using a autoencoder, you can learn the phase transition in the Ising model. So you know that the Ising model is like the model for magnetism. So everything is like random, all the spins are randomly orientated on a lattice. You have no magnetism, and you reach a critical temperature and all the spins align with each other. And now you have magnetism.
Yes.
I don't know. Something similar to me seems to be going on with like 21 centimeters. So maybe you could do something unsupervised where you learn that phase transition by feeding it in these images and images. So you like train it, a series of images at different epochs, and then it learns that transition from neutral to well, when it was previously ionized. Wow, English. I don't know. Does that make sense?
No, that makes sense. That's a really cool thought, and I'll have to look into that.
That should work.
Actually, I think it would be. Maybe we should make a collab now.
Yeah, I think it should work. But I have some questions to ask about the physics. So took a look at the Lapin paper you referred. They don't do a full simulation of the 20 centimeter. They do a bunch of approximations.
Yes, it's a semi-numerical one.
No, I'm not talking about the. Okay. Even for the semi-analytic approach, they do a bunch of approximations. For example, they don't calculate the spin temperature, and they said the factor of the spin temperature minus the T gamma to be 1 assumes that okay, your temperature is decoupled from the CMB, and this is valid and after point, but if you're looking for duration, I think they're going to be, especially at the beginning of reionization, these factors there are important.
Yeah, that makes sense.
Which means that if you try to train your data on these simulations and then you go on the real data, you might run into trouble. That's one comment I have. The second thing is, so correct, and maybe I misunderstood, but your data labeled by the duration and the midpoint of the reionization. Is that correct?
Yes.
But these two parameters, if you want to look into the physics, there are so many degeneracies between cosmology and astrophysics.
Yes.
So what do we do with that? Let's say I'm not giving you a hard time, I'm just trying.
It's really valid points.
We got the data from HERA now, okay? And you run it, and
that would not work. Absolutely.
What would that tell you? That gives that my impression.
Yeah, so this is still all pretty preliminary. Definitely the data that we're using to train is not perfect. There is work being done with 21 centimeter fast, which is perhaps better data. But I think the idea was less that we were going to have a perfect model to predict on HERA data right away, and more, is machine learning even a viable thing that we could use to address this question? A lot of this stuff was still sort of new and trying to, we were still just trying to see if machine learning was a viable thing. This would not, if we got a bunch of HERA data tomorrow and was like, predict on this data, my model would not be the one that we would use. My model's kind of the baby that is gonna hopefully spawn a bunch of, better models that, yes.
I'm just scared, afraid, worried that at the end of the day, you're gonna have to train a network labeled by various cosmological values various values for all the cosmological parameters, various values for all the astrophysical parameters, and train on all of those in order for, after you get the data, you run all the data, and it's going to tell you, oh, omega matter is that, the fraction of stars is that, etc., etc. And I think that's going to be, that seems quite difficult task. I don't know. Are there how to address that?
Yeah, I'm not sure if I 100% understand the question, but I definitely think there's a lot of issues involved in using machine learning in physics in this way. I think that sort of error propagation is a huge problem. The fact that we don't really see what the machine learning algorithm is looking for, the fact that we don't, we aren't.
I'm not talking about the machine learning algorithm. I'm talking purely from the physics perspective. So you can tell how long the duration of reionization was and the midpoint, correct? Yes. But ideally, you want to learn the physical models that give rise to these values, correct? But these models depend both on cosmology and astrophysics. And there is a big list of parameters that and between them there are degeneracies, and it's a complicated calculation. Ideally, you will want a network that's trained on all of these parameters. So when you run into your data, it's going to output the value for each one of them.
Oh, okay. I see what you're saying.
Right?
That is actually something that other people are looking at. There's someone at, I want to say either Berkeley or UPenn who's training on Tau right now. I think we're still at the stage of like, can we even pick out any parameters at all? Yeah, and ideally the future would be to have a model that, you know, is able to pick out all of these sort of underlying degenerate parameters that you're talking about. I think this is still a bit high, like not higher level, but this is a lot more like conceptual. This is the stuff that I'm doing is kind of like, is still just sort of is like, does this physics even like respond to the machine learning treatment at all? But yeah, I think you have a totally valid point in that, like, sometimes the things that we're searching for seem kind of arbitrary and not necessarily like physically informed. And that's something we're gonna have to think a lot about in like training models and stuff. But that's not the part of the research I'm at, and I'm also at the end of the day an undergrad who's really not terribly experienced.
I'm not. Maybe I came out a little bit harsh.
No, it's totally fine.
I'm sorry.
No, I wish I could answer your questions better. If you're interested in stuff like that, I think Professor Poper would probably have like much better answers for you than I do. But yeah, I think that's a really important thing to think about.
Unless there is a way after you get these midpoints in the duration, you can map that to a model and you can extract the data, I guess. So you can do some different kind of analysis on them.
Yeah, that makes sense. Like extract sort of the layers from it and like see what it's doing.
I don't know. I'm just saying words now.
Yeah, there's some techniques in doing that. There's another LaPlante paper where he actually like does a technique where he puts like blank images through the network and then is able to like see what sort of physical features the network is looking for, and therefore like what physical features are given emphasis in this you know, search for parameters. And that's really interesting, but also kind of imperfect in the fact that it's sort of arbitrary, like, oh, it's looking for these structures, but what do these structures mean, like mathematically speaking? So I think that's like, I think it's really hard, right? Because it's machine learning is kind of a black box. So at any time you're using it for physics, it's going to be sort of ambiguous about what the underlying mathematics behind it is.
Mm-hmm. Another thing that you might want to consider is, I don't know if you are familiar with the work by Julian Munoz.
Say the name one more time.
Julian Munoz. So let me send you the.
Yeah, thank you.
So this paper came out last year, and he shows that the one I sent you is a basic one. It shows that if there was a relative velocity between baryons and dark matter, then because of that, you can induce some features in the power spectrum, and they can actually delay the star formation and basically shifts when the reionization happens. So I don't know, maybe it's something that you would like to include in the simulations.
Yeah, I'll take a look at that.
It has a publicly available code called 21 centimeter VFast that does a calculation.
Yeah, for sure.
It's something that you can do.
Yeah, I'll take a look at this. Thank you so much for this paper.
Yeah. But
else I can.
nevertheless, that's really impressive. If you can pick any kind of signal for the reionization from those foregrounds, that's impressive.
Yeah, that's the kind of exciting part. I feel like is that it's yeah, I don't know, it's cool. Anything else I could talk about or clarify or comment on?
Do you have anything else? Kyriakos, anything? Okay, well, I guess in that case, we can adjourn. But thanks for the talk. Great job. Definitely learned a bit.
Thank you, Jasper. Yeah.
Thank you so much. I apologize once again for the time confusion, but I really appreciate the opportunity.
No worries at all. And let us know when maybe you have another update on this new direction you're going, and maybe we can have you give another talk.
Amazing. Thank you so much.
That would be great. Yeah, as soon as you have some new data, I think it's going to be.
Yeah, let us know anytime. You're always welcome to come back.
Awesome. Thank you so much.
Yep, great. Okay, see everyone later.
Bye.
Bye.